Hey, it's Haakan with Topdon. We're going to come back again with another video. This time we're going to show you some stuff with the Phoenix Max, some ways that you can make use of its advanced functions as well as the oscilloscope. So you're wondering, why do I need an oscilloscope? Well, on a lot of modern vehicles, there are far more advanced circuits than there have been on vehicles historically. This has been slowly ramping up over time, and now we are seeing circuits that were once very basic being operated in a much more complex fashion. So in this video, we're going to show you a simple example that might seem like something that's pretty cut and dry usually, at least historically on vehicles, where maybe it's not so cut and dry anymore. Now, if you don't know about some of the terms that we discuss in the video, or you're trying to figure out how to perform some of these tests, there are many different training resources out in the automotive world that can teach you how to do some of these tests. So keep that in mind. But without further ado, let's go ahead and launch into the video here. So again, you're wondering, why do I need a scope? This video is meant to give you just one example of why we need a scope and why we need to know how to use it. So let's go to our next slide here. So, like I said, we're going to be looking at something as simple as a headlight circuit. Again, we've taken that for granted historically and thought, oh, well, headlights are very basic, power and ground, turns on, turns off, right? Let's be careful. A lot of newer vehicles, maybe the circuit isn't so simple as it once was. So let's take a look and see what we've got here. So the advantages you get out of an oscilloscope is you can see what's physically happening on the circuit. That's not something you can do with a standard DVOM. Some DVOMs, like the Curion N2 that we're going to show you in the video here also do graphing. So sometimes you can see those signals with a graphing DVOM, but as we get on newer vehicles, sometimes the signals are too fast even for a graphing DVOM. So one of the other things you want to keep in mind that's really valuable and can help you out in your diagnostic process is the bidirectional control feature on the Topdon Pro Series tools. This can really help you test a circuit without having to go inside, operate the switches, or put the vehicle through another specific criteria in order to operate a given circuit. Oftentimes the bidirectional controls will allow you to turn something on or turn something off and monitor that circuit using other tooling like the oscilloscope. So another thing I just want to point out here is when we're looking at a given circuit, even something like a headlight, if we don't know what an expected behavior is, what is known good, we can always look at the vehicle and see if there is a symmetrical component. So on a vehicle that has headlights, we have two low beam bulbs, one on the left, one on the right. We have two high beam bulbs, one on the left, one on the right. So if we're not sure what's supposed to be happening on the circuit, maybe we have a problem on the left side, which is what we do in this vehicle, and we want to figure out, okay, is the circuit okay or normal? We can go over to the other side of the vehicle where there is no problem, and we can take measurements and make a comparison. This will allow us to understand whether or not what we are seeing on the side where the problem exists is normal or acceptable. So here's the tools we're going to use in this video. We're going to use the Topdon Phoenix Max with the oscilloscope. We're going to use the Tornado T30000 to work as a steady state power supply. Basically, this will hold our voltage steady on the battery even while we are performing testing with the key-on engine off, and it will vary the amperage as necessary to hold that battery voltage steady. So this is very crucial that you have a T30000 or a T90000 to accomplish this when you are doing electrical testing. We're also going to use the Topdon TC003, which is a thermal imager, but it is also a compact Android tablet. Now, we're not going to use the thermal imager in this particular video. We're just going to use it as an Android platform to operate the software of the Curion N2 Neuron. So the TC003 is an awesome tool, and of course you can install other Android apps on the TC003, which will allow you to make even greater use out of a great tool to begin with. So again, in this example, we're going to use the TC003 as the screen and app for the N2 Neuron. Here's the vehicle. So we have a 2015 Volkswagen Jetta. The left front headlight is not working. So we're going to take you through the diagnostic process and show you what we did to fix this vehicle and to verify that there was, in fact, nothing wrong with the circuit for the headlight itself, that it was only a bulb failure and nothing more. So as we walk through the video, I'll walk you through the steps so you can see what the process looks like and use this same logic and process when you are analyzing or testing other systems on a vehicle. So the first thing we're going to do is pre-scan the vehicle. Okay, so now we're going to take you over here and show you the pre-scan of the vehicle. So we're hooked up. We're going to go ahead and pre-scan. We're going to time-lapse this real quick so you can see. We're going to retrieve all the fault codes and get through it real fast here. And then we're going to run the report. So again, super fast time-lapse just to take you through the pre-scan process. This is the only fault code we have. The central electronics module, code 00978 for the left low beam headlamp bulb. This matches up perfectly with our symptom, which again, our symptom is our left front headlight is not currently working. So what do we want to do next? We're going to go look at the factory wiring diagram. So let's go jump and take a look at the factory wiring diagram. Okay, so now we're over here and we're going to take a look at the factory wiring diagram. So we obtained this using the factory website, paying for the subscription. So we're going to show you the wiring diagram for the headlight system on this vehicle. So this is the 2015 Jetta. We did have to use the VIN number to determine which options this vehicle had and the build date in order to find the correct wiring diagram. So now we're on the correct wiring diagram here. We have J519 up at the very top, which is the control module known as the central electronics control module. Then we've got the bulb, which is labeled M29 for the low beam headlamp on the left side of the vehicle. And then we have some wires going to the headlight assembly, which is labeled MX1. So that is basically the whole lens housing that has all of the bulbs in it, including, of course, the low beam headlight. So we've got a couple of wires that we are going to focus on here. So we've got a black and yellow wire going to the top of the headlight here for the low beam bulb. And then we've got a big brown wire coming from the bottom. Now, if you look at the wiring diagrams on Volkswagen, these little numbers you see here is indicating the gauge of the wire. So bigger numbers indicate fatter wires. So we have a 1.5 millimeter wire here on the top for the power and a 2.5 millimeter wire on the bottom for ground. We can also see the ground wire is shared across all of the bulbs. So right out of the gate, that's going to give us a bit of a hint here that if we had a significant problem on the ground, it's unlikely that we would have functional bulbs across all of the headlight assembly if they all share a ground, right? So that's one thing to think about and kind of keep in mind as we go through our testing here. We do have a power supply wire that's coming from the top. If you don't know about Volkswagen, they will typically put the power on the top of the diagram coming from the top and the ground down on the bottom, and brown is frequently a ground on Volkswagen vehicles. So not always, but just a little hint if you were not aware of this fact already. So let's continue on. So here's what we're going to do in our testing protocol here. I'm going to connect our Pro Series Topdon Phoenix Max, and we're going to go into the address word 09 for central electronics, and that's where we're going to go and find actuation tests or bidirectional controls. That's how we're going to turn on and off the circuit to determine if there's a problem with the circuit itself. We're going to use the Curion N2 neuron to identify which pin is which pin down at the headlight connector, because they're not labeled. Volkswagen often does not provide pinouts for a given component like this, so we may not be able to find the pin assignment, so we can use the DVOM to figure out which wire is which. Then we're also going to plug in a substitute headlight of the same wattage as the bulb that normally plugs in. You could just get a replacement bulb and use that, or you could use, like what I have, which is a fog lamp of a 55 watt variety inside a housing that has a heat sink on it, so that I can use this for repeat testing on multiple circuits on any vehicle I should need to do this. We're going to load the circuit, and then we're going to perform a voltage drop test while the circuit is active and loaded down with the substitute headlight or fog light bulb. Then we're going to repeat the test on the other side of the vehicle with no faults. We know the right side is working normally and there's no fault codes. And we'll be able to see if the voltage drop is the same. Now, we're not going to actually show that part in the video. We're just going to keep it brief, and we're only going to show you what happens on the left side of the vehicle. Then we're also going to use the oscilloscope to show you what is actually happening on the power side of the circuit for the headlamp bulb. Because as you'll see in our voltage drop test, the voltage drop that we measure seems higher than we would expect or what is normally deemed healthy on a good circuit. So I'll move my little bubble so you can see that there at the very bottom. But you'll be able to see that essentially the scope is what allows us to determine that that voltage drop is okay, that there's nothing wrong with the circuit. But again, keeping in mind that we can compare the left side to the right side and then have valid data telling us that there are no problems with the circuit on the driver's side where the bulb is burned out and where we have a circuit fault code, right? If we compare the driver's side and the passenger side, it allows us to see if we're measuring the same thing happening on both sides of the vehicle, plus or minus 10% deviation, then we know that the rest of the circuit is normal, right? So again, we're going to take you through that in the video here. Okay, so like I said, now we're going to go identify the pins down at the headlight connector. We don't know which one is power and which one is ground. So we're going to use the Curian N2 to determine which one is which. So here we go. Let's go into the video and you'll see what we're looking at here. So we're going to have our N2. The black lead is going to be plugged into the C or common receptacle on the N2 neuron and clamped on battery negative at the other end of the wire. And then we're going to use the red lead on the N2 neuron plugged into the V for voltage. And then we're going to probe one of the two pins at the headlight connector with the other end of the wire to determine which one is power and which one is ground. So let's watch our video here and we'll see that process play out. So we are plugged in. We're checking the first wire. Again, we've got our negative black lead plugged in over here at the battery and plugged into C for common. And then we've got our red lead for V for voltage plugged in at the V terminal. And then we are probing one of the headlight connector terminals. We are measuring 0 volts. Now you're wondering, okay, what does that mean? We're measuring no voltage difference. There's no potential difference. It's essentially performing a subtraction. So what we have here is we have a difference of 0 volts, which means this is most likely a ground. Now we can't be 100% sure because if the circuit is not powered up, we may not be able to determine that right out of the gate. So we need to check the other pin first before we're sure what we're on. So now we're going to plug in we're going to leave our black lead right where it is, and then we're going to move our red lead to the other pin of the connector and see what we measure there. So you'll see me moving the connector here. So here I'm switching it over, and look at that. We have some voltage on the other pin. Now we have 1.96 volts. At this point, it's pretty easy for us to determine that this is a test voltage, if you will, being sent out from the central electronics module. Generally speaking, modules will do something like this where they will send out a small level of voltage to check the circuit for integrity when the circuit is not powered up or active. They may monitor this. Some modules do this, some modules don't. Sometimes you will see this voltage, sometimes you will not. If we're not sure, then the other option we have here is we could run the bidirectional test with the scan tool briefly, and generally speaking, even if we don't have a bulb plugged in here, we should see it send voltage down that wire real fast at least once. So we could use the min-max function on our N2 neuron, and we could hit min-max, and then we could turn the bidirectional test on and watch for that voltage. If we see roughly battery voltage somewhere between 12.5 to 13.8, with the T30,000 connected, we should be closer to 13.8. But if we see something around battery voltage on that wire as a maximum, then we know that that pin that we're connected to is the power supply. If we see no change when we go ahead and run the bidirectional test with just the N2 probed into the connector, then generally speaking, we're going to expect that that is most likely the ground pin. Now again, we'll show you what we're going to do after this, and this will allow you to see how we can be 100% sure that our circuit is working normally by doing a loaded voltage drop test. So we'll continue on in our video here. Now we're going to switch over to the bidirectional test. So we're going to plug in our headlight, which is substituting in, this is actually a fog lamp, but we're going to plug this in substitution for our regular headlamp bulb. You can see the headlamp bulb here in the bottom right of the picture, and we've got our fog lamp, which is the same wattage rating that the headlamp is, 55 watts, and we have plugged in the headlamp into our harness. We also have the N2 plugged in simultaneously using some breakout leads that come in the breakout lead kit that you can get from AES Wave or from Curian. They both sell breakout lead kits that contain something like that. So now what we need to do is we need to go set up our bidirectional control test on the scan tool. So we're going to go over to the Phoenix Max. The process you're going to see here is really similar to the any of the Pro Series. So whether we're on the Max, the Elite, the Plus, the Light 2, they're all going to be fairly similar to this. So we're going to go into the topology screen. We're going to tap on the module 09 for central electronics. We're going to hit enter, and we're going to go into the menu. So you'll see there the tool was just doing an update in the background. So now we are going in and we're entering the module, gives us some information about the module, but we're going to go down until we see actuation test, and we're going to hit OK. Then we're going to hit read by list, and we're going to scroll through our list until we find the actuation test for the low beam headlamp on the driver's side or left side of the vehicle, because that is the side that is having an issue, right? So now we're going to go do that. We've got our fog lamp plugged in substitution for the headlight bulb, and we're going to run the test, and we can see the test turns on. The bulb lights up nice and bright. Now, we know the bulb's lighting up nice and bright, but do we know all the wiring and connections are good? Not 100% yet. So what we need to do is we need to do a loaded voltage drop test. So a loaded voltage drop test is something that's performed when you have that load on the circuit of the headlight bulb or whatever it is that's the load on the circuit. So a blower motor, a headlight, whatever it is that's consuming that current, that energy, that component needs to be powered up when we perform this test. So the first thing we're going to do is voltage drop test the ground side of the circuit. So we're going to connect our black lead of the DVOM or the N2 to battery negative, and we're going to clamp it onto battery negative. It's going to be in the C or common terminal on the N2. Then we're going to connect the red lead to the ground pin of the headlight connector, along with the headlight bulb also being plugged in. So we're going to show you that on the video here. So you'll be able to see what it looks like when we do that loaded voltage drop test on the ground side. So that's the measurement we get. So you're going, is this good or bad? I don't know. If you're not familiar with what is a normal or acceptable voltage drop test, the industry standard, if you look at any engineering documentation, is usually between 2 to 3% voltage drop. So how you would calculate this, there are a number of online calculators you can use to determine, but in effect, 168 millivolts is acceptable. There's no problem here on this circuit. This is completely normal, just as a cliff notes. If you want to learn more about voltage drop testing and what is good versus bad, there are many videos on the internet that are good on this. There's lots of automotive training that can teach you these things. But again, 168 millivolts is okay. Now, another thing we could do if we're not sure if this is acceptable is we could go and set up our headlamp bulb or our fog lamp bulb substitute, plug it in on the other side of the vehicle where there are no problems, and then we could perform the exact same test and compare our results. If the results are within 10% of each other, I am not suspicious that there is any problem on that leg of the circuit. So in this case, the ground side of the circuit. So now we're going to repeat the same test on the power side of the circuit. So you'll see us transition here. So now our black lead is going to come off of the negative terminal of the battery, and it's going to move to the positive terminal of the battery. Then we're going to take the red lead, and we're going to connect to the positive pin of that headlight connector. Well, we still have our substitute headlamp or fog lamp bulb plugged in, right? Then we're going to use our bidirectional control on the Topdon Phoenix Max to activate the circuit, turn on the headlamp, and you're going to see me switching over to the power side here, and then we're going to look at our voltage drop there. And look at that. So that went real fast, so we'll go back a little bit. So we have 1.69 volts of voltage drop on the power side. Now that's a lot. That's something that you might be scratching your head if you know anything about voltage drop and going, wait a minute. So what is it actually telling us? It's telling us that there is a difference of voltage between the positive terminal at the battery, which should be about 13.8 volts because that's what our T30,000 tornado is putting out, and what it is measuring down at the connector where the headlight plugs in. So 1.69 volts is quite a bit of a difference. So do we know if this is good or bad? Let's find out. Again, we can compare our left front and our right front because we only have a fault on the left front. So if we go and we make a measurement on the right front and we don't have more than a 10% difference, then we know that this is completely normal. If we also have, if we also have other tools like the Topdon Phoenix Max oscilloscope at our disposal, we could also take a deeper look at what's happening on that power supply leg of the circuit to determine, is there something going on here why we're measuring a lower amount of voltage on this particular pin? Why are we seeing less voltage at the headlight than we are at battery positive by a decent amount? Let's go look. Let's find out. So we're going to hook up the scope. We're going to set up our bidirectional test. Our headlamp is activated. Now we're going to go ahead and pull up the oscilloscope and take a look at what's happening on the power supply side of the circuit. That looks like a square wave perhaps, right? So as we look at the screen, we can see that it's actually toggling the power supply on and off rapidly. So this means if we zoom in and look at the scope and pause here, we can see the computer's actually switching it from battery voltage, or roughly 12.8 volts, down to turning it off. So no voltage at all. It's supplying 12 volts, then it's turning it off. 12.8. 12.8, turn it off. 12.8, turn it off. 12.8, turn it off. So as you watch, you can see that it's actually duty cycling it. It's a pulse width modulated signal. For headlamps, this is not something we've seen on older vehicles. This is a newer phenomenon, right? Now, depending on your experience in the European world, this may not be newer news to you, but it's important to remember that, again, many circuits that were often considered cut and dry or simple are more complex now. So we see things like this on many modern vehicles where they are doing something more sophisticated. Now, if you want to get into the why they're doing this or any of the other nitty-gritty details, there's many ways you can find that out. We could certainly do some videos on that. You want to jump over to my YouTube channel, the Shotgun Diagnostics YouTube channel. I can do some videos to explain this in greater depth if you're curious. However, we see that it's on time for positive duty cycle, which again, remember, we're on the positive side of the circuit. It's on about 91% of the time. So if we did a little bit of math and we figured out what is 91% of 13.8, don't you think that we'd measure, wouldn't that add up to roughly about what that difference in voltage is? So if we subtract 1.6, 1.7 from 13.8, that puts us at what? Roughly 12.2, 12.3, somewhere in that general neighborhood. And if you divided 12.2 or 12.3 by 13.8, would you expect you'd measure somewhere in the range of about 91%? I did the math. Yes, it's in that range. It's between 88 to 99 or 88 to 91%. That's about where the range is. So we're seeing that voltage drop because it's actually switching the circuit on and off. So this is a normal voltage drop test on this circuit. But again, if we weren't sure about this, we can go look at it with the scope. Obviously, this is an intentional mechanism that's designed into the circuit by the manufacturer. But if we're still not sure, we could go back over to the passenger side where we had no fault codes and a perfectly functioning bulb, and we could back probe the positive wire at that side of the vehicle, and we would see the same pattern, and we could also make the same voltage drop measurement that we did on the driver's side, and we would measure something in the exact same general range, right? Plus minus 10%, because the circuit is operating normally. So now we know, after doing our loaded voltage drop test, comparing the left front and the right front, and also looking at the signal with the scope, that the left front, all the wiring and connections are okay, the ground wire is good, the power supply is good, all the connectors are okay, everything is fine on the circuit. The only problem we have is a burned out bulb. But again, you need to be sure of this before you make a recommendation to the customer, because you need to understand how the system works. And that wiring diagram didn't tell us anything about, hey, this is a pulse width modulated power supply. It just showed a power and a ground wire, nothing else. But we do know that all components that are doing any work have to have a power and a ground. However, the only way we were able to find out that this was a pulse width modulated signal was by using the scope. And again, we can compare that left front and right front and see this. Then we know this is a completely normal behavior by the vehicle. So we'll take you through, we'll zoom in a little bit more just so you can see exactly what's happening. Again, switching the circuit on and off. We were able to identify the pins at the headlight connector using our Curian N2. We're going to move my little bubble here. We were able to identify which pin was which using the N2. We were able to do a loaded voltage drop test and determine that it was normal by comparing the left front to the right front. Again, we didn't show you the test on the right front. You'll have to trust me that the measurements were the same. We were able to use the scope to also see that this is a pulse width modulated power supply from the central electronics control module. It toggles it on and off rapidly, and it does about a 88 to 91% duty cycle when the headlight is powered on. This is completely normal, and there's nothing wrong with the circuit. Doing this test and using these tools, we were able to see that the circuit is completely fine. We don't have any problems. We can install a bulb, clear our fault code, and send this vehicle down the road and be confident that the vehicle will be fixed. So again, using the DVOM, the N2 neuron, and also using our Topdon oscilloscope, we were able to do advanced testing on this using bidirectional controls, and also the N2 able to identify pins easily and determine which wire was power, which one was ground. But again, hugely valuable to have all of this at your fingertips, right? Because we can turn that circuit on and off just using the scan tool. Don't have to have a helper to go in and turn on and off the light switch. Or there's a variety of many other components that you could never turn on and off without bidirectional controls, right? So again, having that power in the Pro Series Topdon scan tools is really helpful, and having that oscilloscope allows you to see exactly what's happening on a circuit when you cannot do that through any other means. So again, we fixed this vehicle just installing a headlight bulb and clearing the fault code, but this could have been a much more complex diagnosis without specialized tooling and without that oscilloscope and the DVOM, the Curian N2 neuron. So hopefully you found this video helpful. I just wanted to illustrate that even something like a headlight circuit is not cut and dry like it once was. So I appreciate you watching our channel here on Topdon. If you have questions, if there's types of videos maybe you'd like to see, hit us up on social media. We'd appreciate it if you'd subscribe to our channel and watch our videos when you can. We always appreciate your viewership, and anything we can do to help you do your jobs more effectively, we are always happy to do that. So again, I'm Haakan, and thanks for watching.